Most people think they know motion. We move every day. We drive, we fly, we walk, we fall. Movement is familiar, almost obvious. And yet flying feels strange. Orbit looks unreal, and speed often feels completely wrong. Not necessarily because they are particularly complex, but because our intuition was never prepared for them. Our sense of motion evolved for slow speeds, short distances, and firm ground under our feet, not for cruising above clouds or circling a planet at thousands of kilometers per hour. This video is not about learning physics formulas or technical definitions. It's an exercise in trying to explain why motion feels wrong to us in the first place, especially in aviation and space. And once you make sense of that divide between real and imagined, a startling amount of confusion just goes away. The first thing our brain gets wrong: you don't really feel speed, you feel change. When you accelerate, your body responds quickly. There is pressure, force, a clear feeling that something is happening. But when movement becomes smooth and constant, that feeling fades away. This is why an airplane whizzing at 900 kilometers per hour can seem almost calm and motionless, while a train moving at 300 can feel downright slow. Nothing changed about how fast it moved, only the acceleration stopped. Your inner ear doesn't record velocities and numbers. It measures disturbance. If movement is constant and unhurried, your body doesn't report it at all. That is what makes speed feel completely unintuitive, the foundation for almost every misperception that follows. A similar problem can be created at altitude. There is a strong psychological tendency to assume that higher always means danger, because we instinctively link height with falling. But altitude itself has no physical sensation. There's no natural feeling about 10 kilometers above Earth. Numbers without reference points aren't experienced. That's why a kilometer and 10 kilometers can feel almost the same to you on a smooth flight. Your body does not register height. It only registers change. In air travel, that means something else altogether. Altitude typically just means safety, not danger. More altitude equals more time, and hence more options. But intuition can't see options. It sees distance. And intuition reacts emotionally, not analytically. Let's push this misunderstanding to its limit: the idea of orbit. Most people think astronauts float just because there isn't gravity, but gravity never disappears. Gravity is still very much there in orbit. What changes is motion. Astronauts are constantly falling toward Earth. They just keep missing it. They're moving forward fast enough so that the planet curves away beneath them. No impact, no surface to hit, or abrupt change in acceleration. Furthermore, because these acceleration cues have disappeared, the brain takes this as weightlessness. Orbit takes out every familiar reference your perception relies on. There's no clear up or down, no floor beneath your feet, no stable frame to anchor yourself. Confronted with that absence, the brain fills in the space with the closest explanation: zero gravity. But it isn't zero gravity. It's gravity you no longer feel. Contrast is what drives depth perception. Your brain, on Earth, is constantly comparing objects, near objects versus far ones, movement against stillness, and subtle shifts in perspective. Those comparisons characterize the depth of the world. In space, those cues start to crumble. Distances get too large, objects get too sparse, motion gets too subtle to register. Even real data can seem flat when your perception doesn't have something to tether itself to. This isn't a failure of cameras or instruments. It's actually just a limitation of scale. Once the environment overwhelms reference, the depth vanishes. And without depth, space ceases to feel real, even when it doesn't. There's a reason why it's so hard to believe. These ideas end up being so hard to swallow, even after you explain them once made sense of. Data and explanations are not substitutes for perception. They compete with it. And perception almost always feels more persuasive than experience. And once something feels uncomfortable, the brain considers that discomfort to be a message, even if the explanation makes logical sense. That is why words such as, "that doesn't seem right," or "it doesn't look real," hold such importance. They aren't arguments. They are signs that perception has not been satisfied. Seeing motion demands trusting models rather than sensations, and that's deeply uncomfortable. We're accustomed to validating reality through experience. If something is fast, you expect it to feel fast. When it is high, we expect it to feel threatening. If gravity is present, we expect to sense that pull. When those expectations fail, the first instinct is not curiosity, it's resistance. Which is why explanations on orbit with respect to speed or scale face skepticism, even when they're straightforward. Not because the words are incomprehensible, but because something like perception never converges with the conclusion. The brain doesn't stop asking for a feeling that never comes. And when it doesn't, doubt picks up. This gap must be reconciled in aviation and space. The spaces are too smooth, too large, and too stable for vision to adapt. So instead of experienced experience is a proof of reality, reality is contradictory. And that inversion seems wrong, even when it's the right thing. We can accommodate this only if we can accept it. To do so involves a transformation most of us are not comfortable making. It's trusting consistency over sensation, behavior over feelings. It means accepting that something is real, reliable, or predictable, even when it never feels so. Once that shift happens, confusion breaks. Not because the world is changing, but rather because finally the work of perception makes sense. All of this misapprehension originates from the same locus. Humans developed for slow speeds, short distances, and solid ground underfoot. Aviation and space disrupt all three simultaneously. Our intuitions aren't broken. They function fine, but not at these extremes. That doesn't have to make us bad at motion. That means we're honest witnesses working outside of our design range. When we wait for experience to cement reality, confusion ensues. Motion doesn't care what it feels like to move in physics. Everything motion does matters to it. Motion itself isn't strange. Our expectations are. When you stop asking how movement should feel and start asking how perception works, flight gets calmer, orbit makes sense, and space no longer seems unreal. Reality doesn't change. Perspective does.